Okay, so let's start. Thank you for coming back for the afternoon session. And I know that we have a number of people online as well. So we are continuing our celebration of David Blackwell's legacy today. And our next speaker is William Massey. Thank you so much for being online here. William is a professor of operations research and financial engineering from Princeton University, and he's an expert on stochastic processes. Whenever you're ready, William, you can share your screen and we can all see you. For those in the audience, in the auditorium today, if you have questions during the talk or at the end, please raise your hand. Either Adam or I will pass a microphone to you so you can ask your questions. Okay. Are we?
Oh, just about there.
Okay.
Fortunately, I tried to stick in something extra at the last minute, but
there's no problem.
But let me just ungroup this. Should be okay. So this ought to work. Okay, so let me get to the beginning and display. Okay, can everyone see that?
Yes, but it's not in full screen yet. Oh, perfect. It's in full screen.
Okay,
thank you.
Okay. So thank you. I thank Ed Weirman for me inviting me to speak here. So I couldn't be there in person. And yeah, because when they were talking about there are a lot of people online, and then I was going to say yes, that includes the speaker. So it's kind of a mixture of personal insights, also research influences, and then also why not have David Blackwell also talk about some of his own work as well. Okay, so it's kind of a mixture of events I was involved in. Also, it's as you see on the slide, there is an interview from David Blackwell's Statistical Science from 1986. And then there were classroom photos taken for Life magazine in 1962. So I'll kind of mix all these together. And then what I found, one useful quote, okay, it's David Blackwell. So what do you talk about? Okay, or, there's so much to cover. So out of that interview, he sort of says this. And so I feel like, well, who am I to disagree? Okay, so I'll just focus on just a couple of things and not try to be exhaustive. And one thing you can't tell in this photo, you notice the fellow on the right who's smoking a cigarette? And what you can't see is that chair, on the table, there, along with the coffee cups, there are a bunch of ashtrays. Yeah, well, this is the early 60s. So I guess a lot more smoking went on back then. So what's an interesting thing to talk about? Okay, so it's a paper he did in 1946. And give you a time frame, he attended the Institute for Advanced Study from 1941 to 1942. And then after that, he went to Washington, D.C., joined the faculty at Howard University. So this is when he was in the D.C. area. So why does he like this paper? Okay, and and there's his notice his says David Blackwell, Howard University. Over there. Here's some of the reasons he said that he liked this paper. Okay. So this is a point where he felt like he was really getting into statistics. Okay, so let's do a quick sketch of how did he, what type of ideas was he thinking about developing proof for this? Okay, so sure everyone's familiar with the IID random variables, and of course what goes along with that, the strong law of large numbers. Now there's a converse that's not quite as well known. I have that here. You know, it just says that if that limit exists, then that means there must be a finite first moment. Okay, so these are sort of the tools he uses, coupled with you have this sequence of IID random variables, and into that you bring in the notion of a random stopping time. Okay, and of course you could think of it as, okay, if every event is like gambling, when do you make a calculation to stop? Okay. And it's got to be where you are currently. And if you stop now, you based it on what's going on right now and in the past history. So once you have that notion of the stopping time, you can now state Wald's theorem. And it's just so basically the IID sum up to the random stopping time is, you know, what should happen. It's just the mean of the, you know, the IID random variables times the mean of the stopping time. Okay. So, what was the setup for the proof? He developed these sequence of random stopping times. You know, it kind of informally, it's sort of like, how long do you go? You know, if you're gambling, how long do you gamble until you stop, decide to stop? And then after you stop to reassess where things are, maybe you'll do it again. And then, you know, stop, you know, make the same calculation for stopping the next time, you know, go on like that. So because IID sequence, these are all IID random variables too. And then you use them to find the following set of random sums. And you just show that those are IID random variables as well. Okay, you have the setup. What do you do? He said, well, I could rewrite the sum of the Sn1 to Sn of k, average over k. I can write as you know, the following products. And then, thanks to the strong law of large numbers, you know that first factor will converge to the mean of x. And the second factor, you know, because they're IID, you know, that converges to the mean of n. But if the you multiply two limits and they converge, then the product converges. Therefore, what you started with converged. Now you invoke the converse to the strong law of large numbers. So that's how you know that that partial sum up until the first stopping time has a finite first moment. Okay. So this is how he liked to look at proving things, you know, like, you know, kind of deep results using, you know, well, conceptually simple techniques once it's framed the right way. Okay. Now, here's another thing he was wanted to talk about. He was a big proponent of the Bayesian approach to statistics. And how come? Okay. And I think there's one more quote here. Now he's saying this, in the 1980s. So he certainly got his wish in the 1990s. With Markov chain Monte Carlo methods. And I just gave a quick overview about what is Bayesian statistics. The following: you start with information, and you have a hypothesis based on the information. And so the prior probability tells you how likely is that hypothesis to be true. Now, once you have a hypothesis based on the information, you introduce more data. And evidence function gives you a sense of what's the likelihood, how to what extent you should believe this data given the current information. And then, for lack of a better word, I'll just call this experiment of putting the hypothesis and this new data together, where you do the following: you compute this likelihood function. So, basically you're saying it's one thing to see how plausible the evidence is given the current information, but how does it look given, your hypothesis along with that information? And now you essentially complete the square where you have this, develop this posterior probability. So you're saying, well, you had a hypothesis and you looked at its plausibility in light of the information. Well, how does it look with that information and new data? Okay. And to be able to make that transformation, that's the Bayesian statistical learning process. Okay. So this is what he felt was him and other pioneers at the time thought this was the good framework for looking at statistics. Okay. So let me just briefly list, I'm sure this is not close to being exhaustive, but here's some of the things he had published papers, areas of published papers in, made contributions to, from Blackwell spaces to renewal theory, Markov decision theory, game theory, dominated convergence theorem for conditional expectations. So it summarizes a lot of the things he had worked on, thought were interesting, or ideas he thought were important. Now I'll go in a slightly different direction. Talk about a different type of legacy. This would be, in terms of the minority mathematicians and statisticians. The impact he's had, directly and indirectly. So Because I would say, certainly in Black mathematics circles, that we would consider David Blackwell one of the greatest, Black mathematicians of the 20th century. And let me first give you this picture. So this was probably taken year, I think it might have been like 2000, maybe 2010, 2009, 2010. But this is the first decade of the Blackwell Tapia Awards, so named after David Blackwell and Richard Tapia. And this conference was really started, the person who really got this going was Carlos Castillo Chavez. This is back when he was a professor at Cornell. So I think the first one might have been like, I guess the year 2000. Okay. And so I figured go with this picture. It's the first decade, and this might have been the last photograph we had, all the winners at a given time. That might not have happened after this year. And so Arlie Petters, who was, well, at the time at Duke University, he won in 2002. Then Rodrigo Banuelos, who was at Purdue, got in 2004. And I got awarded it in 2006. Juan Meza awarded in 2008. And then Trishette Jackson in 2010. So that's the folks in the first decade. So in some sense, we've been given this award, sort of gave us the honor of considering ourselves a part of David Blackwell's legacy. And I use that as a segue to talk about how I got in, sort of the mathematical influences of David Blackwell for me, since one of the areas he was involved in is renewal theory. And if you talk about renewals, these are positive random variables. You use renewal theory to determine the stationary excess distribution of those IID random variables. So lots of times we look at systems where that's the service time and then the stationary excess distribution. That's important. And so we were looking at an infinite server queue. So by we is my colleague Ward Witt, recently retired from Columbia University. And it was back when we were both working at Bell Labs. And at the time, we were at Lucent Technologies. Well, I was at Lucent, and then Ward ended up working at AT&T. But that's another story. So looking at an infinite server queue with non-homogeneous Poisson arrivals, that's the lambda of T. And then general service times. So there's we only assume they're IID positive random variables. We don't put any preconditions on the distribution. And it turns out for an infinite server queue, if you start off, the system starts empty or with some Poisson distribution, for all time, it has a Poisson distribution. And so you know everything just by writing down its mean. And so the first equality was writing that out. You just kind of integrate lambda from T minus the service time to T. Okay. But now with Ward, we had our innovation that we found the second inequality would hold, that you can write that integral, express that in terms of a stationary excess distribution. And so what are you saying? The mean resource demand is going to be the mean service rate times the service time, or excuse me, mean service demand rate times the amount of time, so basically how many news resources are being requested during the time it takes to serve one person. So that kind of gives you the amount of resources that are needed at a given time. But notice, okay, so normally people looked at this where lambda was constant, okay? It was not varying in time. But when you make it non-homogeneous, then you can see there's not only a time dependence on lambda, but there's a lag effect, where it's not just time t minus the service time, the lag is the stationary excess. So you need the stationary excess distribution just to express what the time lag is. And looking at those issues of time lags, we put that to good use to do a patent for a server staffing algorithm. So this is like the 1990s. So our late 90s, our motivation was looking at telephone call centers. So, but to show you how far reaching some of these results can be. So this is looking at the theory of queues with non-homogeneous Poisson processes and general service times. And we have this nice result, built on ideas from renewal theory. That gave us a way of talking about this. Okay, well, that's nice for 1999. What does this have to say to us in, the current day? Well, here was the big surprise that our time lag concept, from the 90s, we discovered front page news of the New York Times this year. Okay. But now it's not about call centers. It's talking about, so the red curve, the infection rates, that's kind of like the arrival rate of patients. And then if you look at the orange curve, how many of them are in hospitals that need ICUs? Okay, so that's sort of like the resource demand, okay? And notice how they show what they say about the orange curve. It's 14 days later. So basically the lag effect that we saw in theory of looking at infinite server queues, they're seeing this lag effect empirically in the data of, patients being admitted to a hospital during the COVID pandemic. Okay. So shows you how far-reaching, these ideas can be, from going from problems with, just problems in renewal theory to problems in telephony to suddenly it's useful for problems in healthcare. In fact, I say that if you'd asked me what queuing theory was in the 20th century, I would have said it's for looking at communications systems and services. Okay. But 21st century, I would say it's for resource sharing services. And reason for the change is that when you think about it, communications are just a special case of resource sharing. So let's move on here. Another thing I should mention, so I've been running these conferences called CARMS, Conference for African American Researchers in Mathematical Sciences. And this is when we've had, I guess we just celebrated our 26th conference this year, and this is from the 20th. I just want to focus on the photo on the left. that was with, okay. So I blew this up because this was the first CARMS conference we had. And from your perspective, it was up the road at MSRI. And right here, here's David Blackwell. So he attended our first conference. So he got to meet. So this is like the first time we ran the conference. And so students were so excited to see him there and, listen to him talk about his work. And also, I wanted to get back to the Blackwell Tapia conference, but this was in 2018. So we sort of brought, Princeton University out in full force to a mixture of distinguished graduate alums, Jamal Pender, who's now a professor operations industrial engineering department at Cornell University, and then Robert Hampshire, who is, his day job is he's a professor in the Gerald R. Ford School of Public Policy at University of Michigan. But currently he's at the Department of Transportation, where he's a Deputy Assistant Secretary for Research and Technology. And I should mention, I was talking to Jamal the other day. So he's wishing he had been there to join you at this workshop, but this year he had son number 3. So he's a busy father right now. Okay. Over here is Ludwig Tangpi, who's my colleague in the Orphe department. He works in stochastic processes more towards math finance issues. Okay. And at the time, these were 2 students in Orphe, Nicholas Johnson and Emmanuel. Emmanuel, since got his PhD, Nicholas was undergrad, but he is now a grad student at in operations research over at MIT. And also before he left, he became not only a valedictorian at Princeton, first Black valedictorian in Princeton's 274-year history. Oh, and by the way, he was the first Orphe major to be a valedictorian, in Orphe's history. So we're very proud of him. But the key reason I bring this up is that one of the speakers, I spoke at the conference, but more importantly, Robert Hampshire was also a speaker at this Blackwell Tapia conference. And he takes queuing theory and looks at problems in smart cities. And so here was a slide of the talk he gave. This was, that year, 2018, we were at ICERM. That's where he gave the talk. Okay. And decision science, parking management. Oh, and by the way, the parking management he was looking at, it was based on data collected in San Francisco. So looking at parking issues over there. So what was he looking at? Say you just have the data of cars just, going down a street, and you can see if they go by an empty parking spot or do they choose to park there. Okay. And so you just model the individual cars as Bernoulli trials. And so you want to figure out what's the probability the driver passes by a given empty space. Okay. So if all the cars going by are Bernoulli trials, that means the number of cars that go by until a car decides to park will have a geometric distribution. And at the end of the day, you'll know how many times cars parked there and the number of cars that went by in between, that'll be the sum of IID geometrics, and there'll be like a negative binomial distribution. Okay. And so let's summarize that. Okay. Okay. Now you notice there's sort of echoes here of, IID sequences, and then you're looking at various stopping times for those Bernoulli trials. So you have these IID geometrics. Okay. So what do we do with this? Well, you notice there's a lot of, symmetry, so a lot of invariants under, a lot of events that are identically distributed. You can just permute, they're IID instances, so you can permute them. So if you have a sample path looks like this, as long as you realize the last one, this is the end of the day of completing the data. So, the last time someone parked, in a spot, all the cars you went by before that, it's not just knowing when this happens. It's not clear the other cars, if they are one that drove by or they stopped and parked, and you can permute all the dots except the last one, and then that's an event of the same probability, identically distributed. So that's why we can make this statement here, that the conditional expectation of what's the status of the jth car, given that sum, which is telling you all the cars that just drove by empty spots, if you know that number, that answer is the same as you condition on looking at the first car that goes down the road. Okay. And it's all J from one, notice that's the first one, and then you're kind of adding together, adding together all that number plus n minus 1 brings you to this position. Okay. So all of those will have the same conditional expectations. Well, once you know that, you can just add all these up and just pull out this factor. And you know what that has to equal. If you added all the things inside, you're adding from here all the way to here. Oops, jumped ahead. Okay, that is the total number of cars that went by the empty parking spot. Okay, that's how you get the sum over here. Okay. Okay, so now you can explicitly write down this conditional expectation. Okay. And you got this ratio. Now notice that it's strictly bigger than the second ratio. And that's going to tell you something too. Okay. Now you probably guessed by now. And so I was just talking about cars and collecting data and figure out what's the probability that somebody passes by an empty spot. And I'm really sneaking up on the Rao Blackwell theorem. And here's how. So we take that top line and saying that this ratio is just the conditional expectation of that first Bernoulli trial. So instantly we can say the expectation of this is just P, the probability that the car passes empty spot. Now, what's surprising is that this ratio is strictly smaller. And so the expectation of that one is smaller. And the reason that's surprising, because intuitively, you might think, well, the denominator is the total number of cars for the day. The numerator is the number of cars that went by the empty spot. So you would think that ratio would be a good estimation of the probability that a car goes past that empty spot. Okay. Well, not quite. Okay, because this expectation gives you the exact value P. Okay. And so let's summarize those results. Okay. That what's nice about Blackwell-Rao is that it tells you that let's start with the central limit theorem, strong law of large numbers. Statement number one, both of these ratios are asymptotic estimators of P, okay? But now here's where real life may cause problems, okay? That, if you think about it, how many cars may end up parking at a spot on a given day? You know, if a car parks there for like 2 hours or something, you might discover you're lucky if 5 cars park there in a given day. Okay. And so if n is 1,000 and if n minus 1 is 999, you're really not going to care. You know, like they're probably going to both do good jobs of estimating what goes on. But if n is only 5 and n is minus 1 is 4, now you might care. You know, that might make a difference. So, so you're creating a better unbiased estimator. What I mean by better, its variance, you know, because of the conditional expectation, we know its variance is smaller than the variance for the Bernoulli trial. And also on top of this, what we thought was the intuitive answer, you know, dividing, you know, using n instead of n minus 1, it's biased. It's a biased underestimator. Okay. So here's a context of, you know, Robert working in queuing theory is applying to smart cities, looking at transportation problems and estimating the probability of someone parking. And then looking at his estimations, he finds it connects back to the Blackwell-Rao theorem or the Rao Blackwell theorem, or maybe I should say Rao paper who came out in 1945 and Blackwell's paper came out in 1947. You know, it all connects back to that. So it's just interesting to be aware of a David Blackwell and not knowing he's a Black mathematician, but also realizing if you work in the area, you can be influenced by his earlier work as well. So, for a wrap up, let me mention one more important legacy of David Blackwell, his PhD students. Now, the superscript, excuse me, for any given person, those are the number of PhD students they had, okay? And then, oh, and by the way, let me know if I may not have updated the numbers of the PhD students the students had produced. And, or if I left out any one of his PhD students also, let me know. Because the only way I could even think of putting it together was making heavy use of the math genealogy database, because that turned out to be invaluable in putting this together. And so you get a sense of the number of students he produced over the years he was there, from the late 50s all the way to the early 80s. Okay. And I'll just leave that up for a few more minutes to get a sense of the, what his legacy was like. Oh, and I happen to know that, for Bell Labs connection, Ed Gilbert spent many, I think after he got his PhD, he then worked at Bell Labs. And he retired around, I guess 1995, about 45 years later. Okay, so I think that's everything I was going to talk about. So one more nice picture from Life magazine. And I'll end there.
Thank you so much. We have time for a few questions. Let's give it a few more seconds for people to digest if they need more time. Okay, there seems to be no questions here. Talk of a lot of clarity. So thank you so much for the talk, William. Mm-hmm. And we hope to have you here at some point in person, but we really appreciate you giving the talk virtually. Thank you so much.
Thank you. Yeah, thank you for inviting me.